How can casinos ensure they always turn a profit, even when individual players win massive jackpots? The math behind their entire business model relies on a single specific calculation: expected value. To understand the math that built Las Vegas, we don't actually need a roulette table. We can prove exactly how this works right here, with 3 simple coins. Imagine tossing a fair coin 3 times. In statistics, we defined a random variable, written as a capital X, as the specific event we want to count. Here, X equals the total number of heads we observe. If we map out every way these 3 flips can land, we reveal our entire sample space. From 3 tails up to 3 heads, there are exactly 8 possible outcomes. Formally defining what you are counting and mapping that sample space is the mandatory first step before calculating any real-world probabilities. Next, we build a probability distribution. This is a map that matches every numerical outcome, getting 0, 1, 2, or 3 heads, to its specific probability. Looking at our sample space, getting 0 heads happens exactly once, giving it a 1 in 8th chance. Exactly 1 head happens 3 times, making its probability 3/8. We can quickly complete the table using the remaining outcomes. Rolling exactly 2 heads also has a 3 in 8th chance, and getting all 3 heads happens just once. So what is the probability of observing at least 1 head? You could manually add the fractions for 1, 2, and 3 heads, but that requires multiple steps and is prone to math errors. We use the complement rule instead. Because the total probability of all outcomes always equals exactly 1, we simply subtract the scenario we don't want, getting 0 heads. 1 minus 1/8 gives us 7/8, or 0.875. Mastering the complement rule allows you to analyze massive data sets where adding up thousands of individual probabilities by hand would be impossible. With the distribution mapped out, we can finally calculate expected value. This is the theoretical average of all outcomes, weighted by how likely they are to happen. Mathematically, you find it by taking every individual outcome, multiplying it by its probability, and adding all those products together. Using our table, this just means multiplying straight down each column to pair the top row with the bottom row. Let's test this out. Pause the video, multiply down each column, and add them up to find the expected value for our 3 coins. Let's check the math. 0 times 1/8 is 0, plus 3/8 plus 6/8 plus 3/8 gives us a raw total of 12/8. That fraction simplifies to 1.5 heads. However, this result presents a problem. You cannot physically flip half a head in a single trial. You will never flip exactly 1.5 heads on one try. The coin will always land showing 1, 2, or 3. This chart clarifies the meaning. Expected value represents a long-term average. If you flip 3 coins a dozen times, the average jumps around. But over thousands of attempts, the average number of heads per turn will strictly flatten out to exactly 1.5. This principle dictates how casinos operate. They calculate the true mathematical expected value of a game, then set their payouts slightly below it, guaranteeing a profit over time regardless of short-term lucky winners. Let's apply this logic. If a casino charges you $2 to play our 3-coin game and pays out exactly $1 for every head you flip, is it a smart investment? Your expected payout is 1.5 heads, meaning a return of $1.50. Your expected profit is that payout minus the $2 ticket cost. Theoretically, you lose 50 cents every time you play. To solve discrete probability problems, rely on these 4 steps. Define your random variable, build a distribution table that sums to 1, calculate the expected value, and interpret your answer as a long-term reality.